Electrodynamics is usually described with great confidence as if all these questions were solved years ago by the great minds of physicists like Maxwell, Einstein, and Feynman. But even those giants of physics pointed out flaws in the existing model, flaws that have yet to be solved. When calculating a charged particle's energy and momentum using Minkowski's energy-momentum tensor, the entire energy, UO, of the electric field is the integral over the volume surrounding the particle. As long as the particle is not moving, there is no problem. But a paradox arises when trying to calculate the energy and momentum of a moving charged particle. Before momentum starts, beta is 0, and the magnetic field is null. But after movement starts, beta is no longer 0. Therefore, the magnetic field is greater than 0. When using the Lorentz transformation, there is an added term in the electromagnetic energy and momentum calculation which gives this. And the momentum is this. But according to Einstein, the momentum should be this. The particle's electromagnetic mass comes out greater by 1/3 than the original stationary electromagnetic mass. Indeed strange. Abrahams and Lorentz noticed something weird. Let's take a neutral particle and a charged particle. The mass of a neutral particle is its mechanical mass, while the mass of a charged particle is the bare mass of the particle plus the mass of the added electrical charge plus the mass of the electromagnetic field created. When accelerating a neutral particle and a charged particle with the exact same total mass, using the same force for the same distance, both particles will gain the same kinetic energy. But how could that be? An accelerated charged particle radiates energy that the neutral particle does not. This additional energy has to come from somewhere. To solve this enigma, Abrahams and Lorentz used Newton's equations and inserted the force of the Larmor radiation term. But Abrahams-Lorentz equations created a new problem, a paradox. According to the new equations, charged particles emit radiation that creates a self-force on the particles and accelerates it. Furthermore, if we look at the equation closely, we see that the integral extends from the present to infinity, far in the future. Thus, future values of the force affect the acceleration of the particle in the present. In other words, the acceleration of the particle happens prior to the application of the force that is accelerating it. Now, that's just unphysical, isn't it? We have only talked about a few paradoxes in classical electrodynamics, but there are more. This shows how incomplete our model of nature is. Feynman said, "The classical theory of electromagnetism is an unsatisfactory theory all by itself. There are difficulties associated with the ideas of Maxwell's theory which are not solved by quantum physics. The difficulties do not disappear in quantum electrodynamics. The problems are associated with the concepts of electromagnetic momentum and energy." A theoretical physicist, Doron Weinfeld, also assumes that the problem lies within the basic assumptions of classical electrodynamics, which are missing a key component, the inertia of the electromagnetic fields. Could this be the solution to end all paradoxes? Check out our next video or read the complete article to learn more.